Welcome back. There are a couple of programming exercises I'd like for us to work on together. Before we do that, I want to talk a little bit about file formats. Because we understand now at least the basics of the syntax required to write to a file in C. But that doesn't really answer the question of, now that we can write to a file, what should we actually write to a file? The examples we've done so far are just arbitrary text or just straight dat values, just going line by line. Corollary question to that is how can we ensure that others can actually correctly read the files that we write? So when you hear to someone referring to as a file format, that's what they're referring to. It's a standard or quasi-standard way of encoding information to a file. So when someone has a PNG file or a PDF or a zip file, that is a series of ones and zeros. Ultimately, that's what it ultimately is, right? In a file. But the layout of that file adheres to a certain standard so that you can write code to both write to a file of that standard and also read from a file of that standard. It tends to include things like the encoding of data. Is it a text file or is it a binary data file? Also things like what types one could expect as we do things. Also, how many types of variables, how big our arrays would need to be. There's various different methods of identifying the file format. I mentioned in Linux, we don't really use file extensions as such, although Windows does attempt to associate applications with file extensions. So on those systems, like Windows-based systems, the name of the file does strongly hint at what type of file it should be interpreted as. Other file formats include what's referred to as magic numbers, or kind of a guaranteed sequence of bytes at the beginning of a file that indicates what kind of file. All JPEG image files begin with FFD8 hex in the beginning. There's a Linux command called file that attempts to use that information. But even if it was a straight text file, you'd still require some sort of agreed upon method of encoding and potentially interpreting the data. We've already used one very briefly, the comma separated value format. It's exactly as it sounds. You have data encoded as text with commas between the individual data fields. More of a quasi-standard than an actual standard, but writing a parser to handle any arbitrary CSV files is actually a pretty complicated piece of code. So for that table we have here on the right of Robert De Niro movies, we could actually imagine a CSV file that perhaps the first row would be a header. It would be a description of what the column headers would be separated by commas. And then each subsequent row would be the data corresponding to those columns separated by commas between them. It gets more complicated when you allow things for arbitrary length data or empty data values. And then the parser becomes a little bit more complicated than that, or having actual commas in your data as well. And full-fledged CSV parsers can handle all of those. We can make a lot of progress with a somewhat fledged CSV parser. There's many other data formats. You may have heard of the JSON file format. It's very popular for web applications for data interchange. It's language independent despite the name implying that it's JavaScript based. It's got these attribute value pairs of text for an attribute followed by the actual value following it. The idea is that you have a parser that you can then query what is the city and you'll get back a result of New York. So a type of database in a sense without actually using a piece of database software. Although it looks okay, that format doesn't look too terrible. Given the nature of the syntax, it's also a non-trivial programming challenge to actually parse those JSON files. There's YAML as another one, and lots of people use XML-based languages for encoding data. Uses the Python-style whitespace indenting rules. It's very similar to JSON. It's actually technically compatible with JSON. It's also a pretty complicated thing to be able to write a parser for YAML files. You can find libraries that are out there. We could try it. I think we could be okay with just parsing CSV files. So I'd like to give this example challenge a try. So it's sufficiently challenged to parse an arbitrary CSV file. If there's no formal specification for the file, we have to kind of try different things and see what comes out as a good result. But if we have a specific CSV file that we can understand that exact data of that exact precise file, then you can actually analyze the data first, the file first, and you can understand what data each row is going to have. And you can maybe make a good guess as to what C data type would make sense for storing or reading in that particular piece of data. So I've downloaded a CSV file from Baseball Reference for the 2016 Chicago Cubs, a completely arbitrarily chosen year and baseball team. And I'd like to see if we can just parse that data. Parse itself isn't really well defined, but can we read that data? Can we store that data in memory and do something with that data? that would suffice for parsing the data. Call this example MLB file, and as part of it, we do have this CSV file being stored here. I mentioned the file extension isn't meaningful in Linux, but in this case, it is a text-based storage of values for which there's a comma separating the individual values here. In Replit, you can actually view these as text files. That's not too terribly bad. It's kind of hard to see it all and understand it all. If you're going to have these programming practices that involve CSV files, my recommendation is you actually go ahead and download them yourself. If you have Excel or an equivalent piece of spreadsheet software installed, they should be able to handle these type of CSV files. It's the same file, it's just being parsed in this format and visualized a little bit better. I think that helps a little bit in terms of kind of seeing all the data at once, maybe getting a good feel for what the data has. Some of these are going to be character arrays, some of these are going to be strings, some of these are going to be ints. We got a few floats in here as well. We can use our knowledge of file I/O to be able to parse this file and at least print out for every player on the 2016 Cubs how many home runs did they have. I think that's probably sufficient to show that we have successfully parsed this particular file. So a lot of this is going to be kind of boilerplate code, and that is okay. We're going to have to specify that there's a file we want to read. Let's call it CSV file, even though the name of that variable doesn't necessarily indicate anything about it. And we got to make sure we get that file name correctly. And because of all the typos I tend to make, let's actually add that correct sanity check of, did our file cannot open CSV file or something like that. Just so we got some sort of sanity checking error message. Did I type it incorrect? Is the file actually what we expect? Now we're going to have this file, and it has this format. There's multiple ways we can do the parsing of it. I think a pretty common sense approach is just to read it line by line, store that in a string buffer, and then parse that string buffer using the string parsing functions we've been using this semester. To do that, you'd have to declare that line buffer. So for storing one file from the line, we've been playing a little loose with how large that line buffer is going to be, but it's sufficient. Let's make sure we can actually print out a line. That's fgetS. We have to pass in the array, the number of bytes we'd like to try to read, as well as then, in this case, the file pointer that we have open, and let's just print it out. Okay, and we do get that first row, that first line in the file. That's pretty promising. That's the header information, so it's actually okay that we printed it out anyway because we want to be done with it at this point anyway. The programming assignment here doesn't really say, how do we know that we're done when loading it? We can check, whether our scanf call completes or not. In this case, looking at the data, we can say that it ends in a player with name final player Fakington, so we can keep reading until we've read that file and that name of a player. Either approach is going to be fine, but that's a way of indicating, yes, this is not going to be a valid thing. So we've read the line buff. We're going to also want to continue to read the line buff as we go. We can read it while that condition is not being met. So let's try a while loop, a do while loop. We haven't done one of those this semester yet, in class at least. Let's get the next line. So the code should be exactly the same there. So just do another fgetS. Let's type it in. We got it here. And now we have that string. We actually have to grab the data that's between the commas. And this part's going to be a little painful because we have to look at our data again and see what we have. A number followed by a position information. So we have to have variables to store this. So we have rank or index. I don't know what that stands for. We have position, that is a certain number of characters. We have the actual name, but there's a space between it. And if we use scanf for that, we probably should store it just as two names. So that's fine. So first and last. We could also use another getS or something like that to grab it, but there's a comma. If we use scanf, we can grab them separately. Age, games played, plate appearances, at bat, runs, Hopefully these are all going to be valid things. No, we can't do 2b as a variable name. So 2b, second base is doubles, 3b for triples, home runs, those are all be integers, RBIs, stolen bases, caught stealing, bases on balls, strikeouts. Did I already batting attempts, I assume, because we did caught stealing, bases on balls. We want to make sure we get this right. Stolen bases, caught stealing, bases on balls, strikeouts, batting attempts, and then based on what I know of the data, having already looked at it, now we start OBP, slugging, OPS, OPS plus. Those are all going to be floats, at least for a little while here. Let's just grab a couple of them. We've grabbed the whole string. We don't have to scanf the entire string. This is a little painful. Let's just grab OPP. That's fine. So just to show that we can actually grab an individual float here. And then this is going to be kind of the mother of all scanf calls. So we're going to scanf the string. That's scanf. It's the same exact syntax as our fscanf, but in this case, we didn't do an fscanf. We grabbed the whole line. Now we're taking that line and we're scanning it for these things. And this is going to be pretty painful, right? So we have the first integer followed by a string with a space because it's name. No, followed by a string with a space for the position, followed by the first and last name, followed by, however many, we're going to have to just count them here, how many integers we have in a row. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then finally followed with a float. This is definitely a good example of code that's not fitting on one line. It's probably not good code for that reason. But then we're just going to want to make sure we're overwriting each value in turn with the pointers to those to overwrite them. That's the pointer to rank. Position as well as first and last are these arrays. So the name of the array itself is a pointer to that first element. And then we just go through the rest. We're running out of space to write this here. This is a little painful. I don't think there's any denying that, but we're parsing a pretty large file. And our editor is pretty good that we use here. Oh, I didn't do a comma properly there. And I think it'll tell us if we did something terribly wrong there. And we have our dual while loop, or our while loop here. How should we get out of this loop? If our first name is, what was it? Last player, final player. Then that's just one way to get out of it. We could check if we've reached the end of the file as well. There's multiple ways we can get rid of it. String comp is complaining because it's technically defined in string.h. I have it with enough confidence now that while it complains about not finding it, the linker is able to find it. And then we've read something successful because we haven't broken out of this otherwise infinite loop. Let's just print the player's name and this many home runs. Because this example has taken us, I think, enough time. We must have still, we still printed out that header. Cool. So those are the players based on whatever ranking was actually there. Oh, that's funny. There's someone who's got an extra space in, poor La Stella. And that's probably going to mess things up for everybody, I would think, if we're going to miss a string. So let's run it again, see if that changes. No, it was only his name that wasn't done correctly. So at least we've parsed it a little bit, right? We have this many things we're reading. That is pretty cumbersome in that, we're having to keep track of all these different variables, and we're making a best effort guesstimate as to what data types make sense. That's why CSV parsing is hard. Even when we see the format, know the format, it's not relatively straightforward. I don't want you to have to worry about pausing the video and looking at every line of text I'm typing. As a reminder, all of these programs I work on during these videos are available in our replit for the class under the in-class portion. You may have to scroll all the way to the bottom to find them, but otherwise they're roughly in order. And take a look at those. And they should provide some hints and some maybe code templates to kind of import into your own programs that you are personally working on. I have one additional in-class programming exercise, which is very close to the programming practices you have for PP08 here, which is to find all the words in a dictionary or the dictionary that are so-called ordered words, and we have to define that to be able to do that, and that's words in which all the letters appear in alphabetical order. So examples are Abbey, dirt, and although it's a little bit subtle, see it almost is an ordered word here. I want you to think about this before we just dive into the code. First off, we're going to have to read a dictionary file. How are we going to do that? How are we going to detect that a word is actually ordered in our code here? So reading a file, there isn't that much to write in terms of our design here, other than perhaps saying, as we're reading a file, what do we know about a dictionary? That can be pretty important. So, if step one is read the dictionary, what do we know about a dictionary? Well, there's, Webster's dictionary that has, words and their usages and their definitions, and we really just want to see the actual words themselves. So maybe it involves some parsing. It depends on the file we have access to. I'll provide some that I think we'll see is relatively straightforward, but that's definitely a task we have to accomplish. And then we have to, what does it mean to be order? How to determine order? We have what's listed in the description there, which is just all the letters appear in alphabetical order. And we can start with the word Abbey that's just listed there, in which we know, and now as we're parsing our individual words here, we know that these are just arrays. Look at that fanciness. Look at it, it's just an array of characters that we can iterate through like any other array. So we can already kind of start to imagine our for loop here, right? For I equals 0, I is less than string length word, I plus plus. We can then access, word of 0 and then word of 1 and then all the way up to word of string length minus 1 that we would have here. We might be able to determine based on just that. If you remember, and so many of our examples have had the ASCII table, an important observation for this kind of example is that the ASCII table is in order already, right? The value for A, or lowercase a, is already less than the value for B, directly so, which is less than the value for C, etc., which is less than Z. We have to check if our dictionary is got a mixture of uppercase and lowercase, but we know how to handle that too, and we should just be able to check that kind of condition. Is word of 0 less than word of 1? Is that less than word of 2? Is that less than word of 3? And if so, we're in ordered, otherwise we're not. Perhaps by default we assume the word is ordered until we find a relation that is not held, and then we say, oh, by the way, it's actually not ordered, and we continue here. Let's give this one a try. We may find this one a little bit less painful to write than the previous example here. So we just have our starter code. I provided a few different dictionaries here. This one looks okay. This one, frequently misspelled words, I believe, and this is just the really big dictionary here of words with, I don't recall how many things we have in this one. Oh, those are star.text caps. Actually, the crossword and the words all is pretty similar. The 1,000 frequently misspelled words is just 1,000 words. The code should be the same, right? In fact, we can provide it as an input to the program, and let's do that this time around, which is not a hard-coded program, hard-coded dictionary that we want to read, but instead, as part of our variables in the code itself, what is our actual file? We need to have some sort of string to hold that file name because we pass a string to fopen. I don't actually know what is an appropriate max length for a file name. That could be a system variable we could query, but let's hope that it's limited to 128 characters for now. So we have just a simple scanf just for the name of the file itself. And if we're going to do that where it's a user input, we should really be careful that, as we open file name, a arbitrary user entered file name, we should probably check, did that work out? And if not, let's not even try the program, right? Cannot open file, and now it's a variable, so it'd be nice to know that in fact we can't open file name. And it's important not only are you checking that, get out of here basically. Return 0, or some error condition. It doesn't have to be 0. You can return -1 if you want to. It'll really give you a funny error when you do that. Here's a file that doesn't exist. It'll say exit status 255. Well, maybe you want that, maybe you don't. From our perspective, just printing out the message and exiting is sufficient. But you can then, from our functions, as we'll see in the next learning module, or just from main, you can actually provide a little hint that there was a reason it failed. It didn't just fail, or it didn't just return. It returned some meaningful message. We don't use that a lot, but hey, for this instance, we'll return a value of 1. And now we have a file that does exist, like freak.txt. It doesn't print anything out. It returns, but not with any error number associated with it. So it's okay here. So we have code to read and potentially check if our file is valid. Now we're back to kind of scanning the file. This file is a little easier to scan than the CSV file. I'm not seeing any spaces. In fact, one thing I can do is check, did it find a space? I find the Replit editor for large files like these isn't that great, but it's telling me it didn't find any spaces in the file. I personally, when I'm doing my own development outside of the Replit environment, I use Visual Studio Code, not just for actual coding, but actually just large text files, and it's got some pretty good features. There's other programs that are really good. People use Notepad++, people like Sublime Text and others. Replit editor is fine and great and all, but for large files, I don't necessarily trust that there was no space in the file. But let's assume there's no spaces in the file, then this is still a relatively easier parsing task than it was before. We don't have to worry about our fgetS and parsing with scanf. We can do that same exact loop we did prior to this, where we read from the thing. We're checking to see that we can actually read something. We have to put it somewhere. fscanf, read from an in file. If it actually did correctly read a word, then we keep going. And that requires us to actually define our word somewhere. Getting a little sloppy in defining variables wherever we want, but in this case, let's assume each word is 64 characters or fewer. This is a good testing spot, right? Let's just make sure we can actually print out the dictionary. Let's do it with the small dictionary. And there's our small dictionary, and it all printed out for us. So, okay, we have code that reads out the entire dictionary. And again, what was our challenge, right? Ordered words. Is the word in order or not? I had suggested that, there's 2 ways to do this, right? You can write code that assumes it's not in order and then proves it is in order. Or you could write code that assumes it is in order and proves that it's not in order. My assumption, I guess, although this is a minor optimization, that most words are not in order. So we should be able to disprove it pretty quickly that it's not. And going back to our brief digital whiteboard here, like I said, we can just kind of iterate through it from 0 to string length. And once the current letter is not less than the next letter, we're done, right? It's not in order. We can get out of at least that word and move on to the next word here. So that can be our int I loop. And it's complaining about the header again. Again, I like to get rid of all my red squiggly lines here. If word of I is greater than word of I plus 1, they're in ASCII order. Then, in fact, we were not in order. And we don't need to keep looping anymore. As soon as we find the first counterexample, we are done. Little bit of a caveat here. We can get out of this inner loop at least, not the outer loop as of yet. Little bit of a caveat here. We saw this in a prior sorting example as well. We're comparing I to I plus 1. We always want to make sure we don't accidentally go beyond the length of the array. We don't actually have to compare that last letter to anything. It's all the previous ones we have to compare to it, but we don't have to compare it to anything. So we can iterate one fewer time through that loop. So we are done with that loop one way or the other. So if in order is equal to 1, let's print out the in order words. So that should be significantly fewer words. That's still quite a few words are in order. Go, no. Oh yeah, those are all in order. I guess it's not that hard to be in order. Let's limit the amount of words we're printing out to some interesting ones. Maybe ones that are of a certain length. So if it's in order and the word is sufficiently long, you could argue we shouldn't even check the word if it's not sufficiently long, but no harm. We check them all and we're only going to print them out if they're greater than 5. And then there's only 5 or String length is greater than, yeah, there's only 5 words of length 6 and none any longer in that list of 1,000. Let's run it on the whole dictionary then. And it found quite a few that are of size 6 or greater. Just out of curiosity, there's at least one I see of size length of 7, and only one in the whole full dictionary that is of 8 letters, that has all the letters of the word in alphabetical order. So that's an interesting little observation. Whether or not that's super relevant or not, I don't know. But our code was able to solve that for us and kind of solve it, instantaneously for. And I think that's just a good example of the power of writing C code and the power of being able to read from files versus just trying to provide our input via some other mechanism. The only input we provided there is what's the name of your file, and I was able to very quickly parse through the entire thing and very quickly determine whether the words in the file were in alphabetical order or not. Let's leave things here for right now. Our next topic is going to be looking at functions. It's kind of a funny topic in a sense, as we already know functions. We've been calling functions left and right. It's more about user-defined functions. Maybe you've already done this a little bit in your code. I think you'll see that it can make certain programs you write a lot cleaner and easier, and easier to modularize and kind of build bigger parts from the individual pieces. But there's not that much that's new for writing functions, so it should be a relatively straightforward topic for us, and just yet another opportunity to get more practice in writing fun programs. Let's leave things here for now, and I'm looking forward to seeing your programming practice for part 8 here.